Okay, reading quiz 5 is about area between two curves. Well, what does that mean? If before we've talked about finding the signed area between one curve and the x-axis. Now we talk about finding the area between two separate curves. Our area is not necessarily going to be signed. We're talking about positive area, just as we would talk about the area of a circle or the area of a rectangle. Now we're just dealing with unusually curved shapes. The shapes are formed by functions, which are just regular functions. So first, let's create a formula, which we talked about in our lab. Earlier we found the area underneath a function. Now we expand this idea to find the area between two functions. And I've got two examples, one function in red and one in blue, on the picture below. What I've done is I've created rectangles, just like we did with the Riemann sums earlier when we were formulating our idea of what the area between the curve and the x-axis was. And notice that it's the same idea. We're just finding the areas of each of these rectangles. Well, what's the height of each of the rectangles? The height of each of the rectangles is the difference between the two functions, and the width is just our minute delta x, or change in x, or dx, as it was when we were doing regular Riemann sums. So what we say is that the area bounded by continuous functions f of x and g of x, and the lines x is equal to a and x is equal to b, with a being the lower value and b being the higher value. Also assuming that f of x is bigger than or equal to g of x, we get the integral from a to b of f of x minus g of x dx. Well, let's see this formula in action. Find the area bounded by the function y is equal to x plus 6, y is equal to x squared, x is equal to 0, and x is equal to 2. 0 and 2 will provide our endpoint limits of our area here, the left and right limits. X plus 6 is the higher function, x squared is the lower function in this case. So step 1, always try to draw a picture representing the situation. Oftentimes you'll be given a picture, sometimes you'll have your calculator, other times you'll be relying on your own knowledge of what the functions look like. Step 2, determine the limits of integration. In this case, you've got an easy task because the limits are determined by the vertical lines that bound the function. X is equal to 0 and x is equal to 2. So our limits will be our lower limit of 0 and our upper limit of 2. Step 3, use the formula to solve the problem. Note that f of x is equal to x plus 6 is the top function, while g of x is equal to x squared is the bottom function. So we want to find our height by subtracting f minus g, since f is the higher function and the more positive value. So our area would be the integral from 0 to 2 of x plus 6 minus x squared dx. These are relatively simple antiderivatives. We get x squared over 2 plus 6x minus x cubed over 3. We want to apply our FTC. Plug in our values, we get 34/3. This is the positive area, not signed area necessarily, between the two functions rather. Example 2. Find the area bounded by y is equal to x plus 6 and y is equal to x squared. Well, wait, didn't we just do that problem? How is this example any different from number 1? Well, if you noticed in number 1, we had the lines x is equal to 0 and x is equal to 2. Those were our determined bounds for the function. Typically, when you see a horizontal or a vertical line, that will determine our limits of integration. In this case, we don't have them. So we draw a picture to help us see what's going on. And notice in our picture that these two functions cross at x is equal to negative 2 and x is equal to 3. Those two values form our bounds for our area. Okay, and they will be our limits of integration. There are intersection points. So in order to find these by hand, we would just set x plus 6 equal to x squared. When we go through and we solve, we get x squared minus x minus 6 is equal to 0. And our two roots are negative 2 and 3. Those determine our bounds for our function. And so now we can use our formula to solve it. F of x equal to x plus 6 is still our top function. X squared is our bottom function. And we're going to integrate from negative 2 to 3, which is a wider region. In doing so, we find the same antiderivative, and we get 125 over 6. We choose this area, by the way, because none of the other choices for our limits would actually create an area that's bounded by the two functions. They would create kind of open spaces. Example 3, find the area bounded by y is equal to 8 over x squared, y is equal to 8x, and y is equal to x. And notice that you'll have to break up the region. Why is that? So again, we've got our picture representing our situation, and we want to find the area bounded. Again, the area bounded is not, it can't be anything other than this region because all of our other regions that we have are open spaces. So we get this kind of triangular, curved on the right side sort of shape. So we've got to be careful when we determine our limits of integration. Because if you notice in the blue area, we've got y is equal to 8x on the top and y is equal to x on the bottom. But once we get that through that point of intersection at x is equal to 1, at the very top of our picture, we notice that the function y is equal to 8 over x squared now becomes our top function. If we were to continue to use y is equal to 8x as our top function, we would have problems because that doesn't form the boundary of our region anymore. So we need to divide this into a blue area and a brown area in this case. In our blue area, we've got y is equal to 8x on the top and y is equal to x on the bottom, and that goes from x is equal to 0 to x is equal to 1. In the second region, we've got y is equal to 8 over x squared on the top and y is equal to x on the bottom, and we're going from x is equal to 1 to x is equal to 2. Now that we understand that we've got two separate regions, we're going to use our formula to solve the problem. In this case, we want to find the area from 0 to 1 of 8x, top function, minus x, bottom function. That's the blue area first. And then the integral from 1 to 2 of 8 over x squared minus x, 8 over x squared being the top function, x being the bottom function. In this case, you could solve it by hand or with your calculator. You find out that the area of the region is 6. This would typically be a problem that you would not have your calculator for. I just needed to save space and I don't have all the work for it there. A second thing you can do is integrate with respect to y. Well, what does that mean? Well, if we orient our rectangles vertically, meaning that we're stacking them vertically, we can integrate with respect to y if our functions are solved as x is equal to y something. In this case, you'll notice that our rectangles go from a very bottom part all the way up to a very top part. In this case, we might say our integral goes from, let's say, -3 to 3. So our area bounded by continuous functions f of y and g of y, with f of y being the farthest right function, in other words, the one that's farthest along the x-axis in the positive direction, and the lines y is equal to c, which would be something like -3, and y is equal to d, which would be something like y is equal to 3, would be the integral from c to d of f of y minus g of y dy. Again, our top function, in quotes, is the function that's farthest to the right. G of y would be our bottom function that's farthest to the left. C is our lowest limit, and D is our highest limit. Note that everything, including our limits and including our functions, is in terms of y. So let's see this in action. Find the area enclosed by the line y is equal to x minus 1, and the parabola y squared is equal to 2x plus 6. So first things, we draw a picture representing the situation. If you're using your calculator, you'll need to solve for y. With the parabola, you'll get a positive branch and a negative branch, so be careful about that. Determine the limits of integration. Remember, our limits need to be in terms of y. So we need to find the intersection points that bound these to the line in the parabola. Our intersection points are -1, -2, the very bottom one, and we've got an intersection point at 5, 4, our one on the top right. Our limits need to be in terms of y. So what are we going to use? We're going to use the y value of -2 going all the way up to the y value of 4. And again, in this case, we're stacking our rectangles going from -2, in our case here, to 4, as we just saw. Use the formula to solve the problem. So we notice that the line is farthest on the right. That is our top function, just as it was when we were integrating with respect to x. In this case, we need to solve for our function in terms of y. X is equal to y plus 1. Similarly, we need to solve for x with our parabola. X is equal to y squared minus 6 over 2. So our top function is the y plus 1. Our bottom function is y squared minus 6 over 2. So we subtract the two of them, and we're going from y is equal to negative 2 to y is equal to 4. Notice everything's in terms of y. Notice that we're using dy. And in this case, I think we just used our calculator. You can type in terms of y if you want, but you need to make sure that everything is in terms of y, or you can just convert everything to x and let your calculator do the work on that. You get 18 as your final answer. Example 5. Find the area bounded by y is equal to 2 and y is equal to 1 over root x and y is equal to x. So I've got two pictures of the regions here, one that's zoomed in and one that's not. We can approach this in two different ways. We can try to find this in terms of x, but if we do so, if you look at the rightmost picture, we're going to have to divide the region into two parts. The line y is equal to 2 is always on top, but on the left region, we've got y is equal to 1 over root x on the bottom, and on the right region, we've got y is equal to x on the bottom. So we would need to divide it into two different regions. If we find this integral in terms of y, however, we only have one region that's going to go from y is equal to 1 to y is equal to 2. In this case, it may be easier to solve for this integral in terms of y. I'll leave it up to you to decide whether it's easier. So use the formula to solve the problem. If we have our formula in terms of y, our formulas for our functions are now the rightmost function, which is x is equal to y, and our bottommost function, which is x is equal to 1 over y squared. How do we get that? We solve the middle function, y is equal to 1 over root x, for x. Notice our limits are just between y is equal to 1 and y is equal to 2. And we're going to do our top function, which is the rightmost function, in this case, y minus 1 over y squared. When we solve that, we get 1. On the other hand, if we were to solve in terms of x, we would have to go from 1/4 to 1 with the function y is equal to 2 on the top and 1 over root x on the bottom, and from 1 to 2 with 2 on the top and x on the bottom. We get the same answer, of course. Well, notice we have to deal with two different integrals, which is a little more complicated. So the point is, what do you need to do when you first see a problem like this? Decide whether or not it's easier to integrate with respect to y or integrate with respect to x. You always need to look and see which are top functions and which are bottom functions, and if they change somewhere in our interval. In this case, when we integrate with respect to y, we have no change. That's good. When we integrate with respect to x, we have a change. There's a change in the bottom function in this case. And so we have to deal with two integrals. It all depends on your preference. Example 6. Let R be the shaded region bounded by the graph of y is equal to natural log of x and y is equal to x minus 2. Find the area of R. And the shaded region should be the region between those two functions there. And our answer, to find the points of intersection, we need to use a calculator. This would definitely be a calculator active question. We would find two points of intersection at A is equal to 0.159 and B is equal to 3.146. The AP exam requires you to round to 3 decimal places, but only in your final calculation. So what you need to do is take those A values and your B value and store them as soon as you get them. We can show how you do this in class. So we store these on our calculators. If you write down on your exam that so 3 decimal places what your A and B values, you can then use them throughout your problem and just write A and B without having to write all the digits, as you can see in the integral below. We find the integral from A to B of natural log of x minus 2 dx. Remember to keep your parentheses. You can store your functions as y1 and y2. It makes things a whole lot easier. And we get 1.949.